The stall will be created because of that. Is there any reason for another stall? Stall may also occur because of the data dependencies. That if the instruction, if one instruction result is depending upon the previous instruction, it all depends on the previous instruction. This is called as dependencies. Got it or not got it? Now I'll explain this with an example. So let's assume Fatma wants to have an Emirates ID. Siraj also wants to have an Emirates ID. And Farah also wants to have an Emirates ID. Okay, she goes there. Okay, so what's the first step? Take a token. Should she take a token? Then she goes to the next stage. She take a picture. Then she goes to the next stage and then she's making the sign. And the fourth stage, she make a payment. Yeah? Okay, if Fatma has money, she will go through like completely, she's not dependent. But if Fatma is now dependent on Farah, and all the money is with Farah, and Farah is back in the queue. So when she reaches there, she say, okay, the immigration guy tells her, oh, please give me the money. But she doesn't have the money. The money is with whom? With Farah. So she has to go back to the Farah. So what will it create? It will create a stall. It will create a latency. Above in the pipeline. You got it or not? So the pipelining bubble occurs because of what? Dependencies. Clear? Any question? Okay. So now, okay, please remember we have all these things. So please look at how does pipelining work, properties. We have three classes of instruction: load and store, arithmetic, blah blah blah, branch instruction. This is the 5 stages, PC plus 4, decode stage. We have the memory reference instruction, the register ALU, the register immediate, we also did it. Then we have the memory instruction, memory stage is used for the load and store instruction, and then we have the write back cycle. And it's also used for register ALU or the load instruction. Which instruction is this? LDR. So it goes there, NPC, IR, then it goes to A and B. A will be base R, signing station of the offset. We compute the base R, signing station of the offset, effective address, and read values of the memory. Clear? This is now LD. Please remember, this is NPC. NPC1 or NPC2? Here, NPC1 or NPC2? Load, LD, NPC1 and NPC2. So this is NPC2. This is ADR-SR1, A is SR1, B is SR2. This is all the like the new units. We did it. Please remember we already did it. Can you see here? This is how instruction moves to the pipeline. So this is instruction I, fetch, decode, execute, memory, write back, and it goes through the pipeline. And typically, please remember, the speed up if there are no stalls. If there are no stalls, what is the speed up? Okay, please remember. So, I'll explain the speed up formula. This is very important. This is very important. Assume that we have 10,000 instructions. How many instructions are there? 10,000 instructions. And we have 10,000 instructions. And assume we are using a sequential machine, not a pipeline based machine. Okay? And there are different stages. So each instruction will take how many clock cycles? Each instruction. 5 clock cycles. So each instruction take 5 clock cycle to execute. And please remember, there is no pipelining. What will be the total latency or total clock cycles in a non-pipeline machine? Non-pipeline. Yes, help me.
10,000 times 5.
Yes, 10,000 times 5. How many clock cycles?
50,000.
50,000 clock cycles. 50,000 clock cycles. Because the thing is, so now we can say we have fetch, decode, execute, memory, and write back. This is instruction 1. This is my I1. when I2 should start? I2 should start from here. I2 fetch, decode, execute, memory, and write back. It also take 5 clock cycles and 5 chrono. So it means it will, the total number of clock cycle will be 50,000 clock cycles. But if we have a pipeline machine, with a pipeline, please remember, what will be the total clock cycle? In the absence of stall, no stall, there are no stalls. 10,000 plus what?
5.
Plus 5 number of stages, D
Minus 1.
minus 1, what is that thing? 10,004. So if you look at here, if you divide this 5,000 with 10,000, what is the speed up? So it is actually, the speed up is actually, how many speed up? It's actually 5,000, 50,000 divided by 10,004, and it is equal to, approximately equal to what? Approximately equal to 5. It will be actually, if you calculate it, it will be actually 4.99 plus something like that, which is approximately equal to 5. But the problem is that, now, here we are assuming that there are no stalls. But if there are stalls, so if there are stalls, so it means that now in this case, what is the total number of instruction? KR number of instruction. What is this thingy? Help me. What is 5? No, not stages. What is it? Is D and minus 1. This is actually total clock cycle in pipelining, which is called as ideal pipelining. There is no dependencies, there are no stalls. But again, let's assume that there are 100 instructions. Each instruction take 5 clock cycle and 5 cycles to execute. It means that now the pipelining D is now 5. Assume that we have stalls, the number of stalls. Let's assume the number of stalls is 2000. There are 2000 stall cycles. So what is now the total clock cycles? Or maybe 7000. What is now the total clock cycles? Help me. 10,000 plus what? Help me. 5 plus 7,000 minus 1. So this is what? This will be what? 17,000 004. And what is the speed up here now? Help me. 50,000 divided by 70,004. Can you anyone calculate, please? Help me. Yes. Can anyone calculate? Yes. You're too slow. Yes.
2.94.
No.
Yeah.
2.94. So it is actually approximately 3 times faster now. So basically, in ideal pipelining, there will be no stalls. Okay, now what are the reasons of stall? What are the reasons of stall? Number 1, what are the reasons of stall? Help me. What are the reasons of stall?